Hi all, this is Mr. Yeager for chemistry with our third lesson in our atomic structure and nuclear unit. This one we are looking at the one big calculation we're going to do in this particular unit, and it's average atomic mass. So at the end of the last unit, or last video, we were looking at, we finished up with isotopes, and we now know that again all atoms of an element are not exactly the same. They might have different masses, all right? But they are all of one type of element. And it turns out that when you get a group of these atoms together of a single element, there's a general percentage of atoms that are going to be one mass, another one's going to be another mass, another one's going to be another mass, okay? And therefore, when we get something like that, it's like your grade average, okay? Your grade is going to be made up of both your summatives, which is your tests and your projects, and the formatives, which is your quizzes and your other assignments, your labs and things like that. But we know that your grade really is more represented by the tests. That's what's happening here with average atomic mass. It's a weighted average based on what mass is the most prominent within a group of atoms of a single element. Again, we're talking about of a single element. Okay? So we calculate out what's called this average atomic mass. Okay? And again, some isotopes are more abundant than others, and so obviously they can affect that average atomic mass to be a little bit closer to theirs, just like your test average is closer to your real average versus maybe your quiz average. Okay? All right, so we do have something called percent abundance, and this is just the term saying, as it kind of describes, how abundant is each type of isotope. Okay, which isotope occurs more frequently than another one? And this might make sense when we start actually doing some problems. Okay, we're going to use this in the calculation of our element's average atomic mass. Now, I want to point this out right away. Okay, we can at least create a good prediction of what mass of an isotope is the most abundant looking at the periodic table. So I'm going to bring back the calcium one again, where we had Ca20 and then this was like 40.08 or something like that. I'm going to actually double check. I want to say it's 40.08. And I mentioned that this bottom number is the relative atomic mass, or the average, relative is another word for average, is the average atomic mass, okay? And so what you can kind of predict is you can go, okay, if the average atomic mass is 40.08, what whole number is probably the greatest? What mass number, which is again a whole number, is probably the greatest for calcium? Okay, well what whole number is closest to 40? It would be calcium 40. Okay, so we can predict that probably the most abundant isotope for calcium will be 40. Calcium, I believe, has calcium 42 and calcium 44 or something like that as well, but you can tell if I weight average all three of these together, clearly this one must be taking over, pulling the average down so much closer to it. This would be like the test, and these would be like the quizzes. It's closer to what you got on the test versus what the quiz grades are. Okay? So that's what we're looking at. You can make a slight prediction. Now, that's not always correct because, as you saw on the prior slide, some elements have 30 isotopes, and that can make some crazy averages and go all over the place to try to make that work. Okay? So this is your formula for it. I know it looks kind of intimidating. Basically what you have here is you have to take each isotope one at a time, and you multiply the percent of the isotope times its mass. You then do the second isotope, its percent times its mass. You do the third isotope, percent times its mass, and then you simply just add them all together. Okay? And that'll be your average atomic mass. Now please remember, when you have percentages, and you have something like it's 82.4%. We need to change this to a decimal. To change a percent to a decimal, we should just move it over 2 spots, so 0.824. And that's what you would put in for your calculation, okay? I usually see people don't mess up those. It's when, you're gonna get ones where the percentage might be 0.34%. Well, you don't plug in 0.34, you're gonna plug in 0.0034. Okay, so you move the decimal point over 2 times. We should know that. All right, so there it is. It tells you right there. Sorry, I didn't even pay attention with the next slide. So you can take a look there. Obviously, move it over 2 times. Okay. All right. So, I mean, here's an example. I'll let this one kind of go out, and then we're going to do maybe 1 or 2 more in this video. So let's say you have these 2 isotopes, okay? And you can see one has a mass of 6.1015 with a percent abundance of 7.5, and the second one has a mass of 7.016 and an abundance of 92.5. I don't want to get too technical with this. We would technically say this has a mass number of 6 and this has a mass number of 7. Technically, these isotopes aren't exactly at whole numbers. So if I give you a number where it has with a decimal with it, include it, like 6.015. Don't just leave it as 6. Don't change 7.016 to 7. Keep those numbers and plug them in exactly as seen. If I do just give you that you have isotope X6 and isotope X7, then you could just put 6 and 7. So it just depends on how the problem is written, okay? If I give you the mass, use the mass as given, okay? Oh, sorry. All right, so you can see the steps coming in here. You're going to turn the percentages to decimals, divide each one by 100, and then you're going to multiply each mass times its abundance, its decimal abundance, and then add them up. So let's see that happen. You do 6.015 times 0.0750 plus 7.016 plus times 0.925, and the answer is 6.941. Okay? Yes, you could possibly figure out what element I'm talking about by which element has the closest value to that you'd look at the average atomic mass at the bottom of the element box, and this one would be lithium. Okay? So let's do a couple more real quick. That's the end of that one. All right. I'm not going to do all of these, but we'll do a couple. All right. This one's already pretty tough because there's a lot of them. But you just put all of it together. So it says calculate the atomic mass of lead if the 4 isotopes have these values. 203.973, 1.4%. I'm not going to read them all out. What I'm going to do is I'm going to put these together. I'm going to be multiplying the mass times the percentage, but I need to change the percentage to a decimal. So I would put in this 203.973 times 0.014. Okay, I'm not going to do this too often because, guys, we really should have no issue with this, of moving it over 2 times, the decimal. So there's that, plus, I go to the next one now. I mean, the big thing is that you don't accidentally mix them up. 205.974 times 0.241, 12, plus 206.976, parentheses, times 0.221, plus 207.977 times 0.524. What does that equal? Sorry, I gotta put this all in my calculator. It'll take me a second. I'm getting 207.217, and the units would be AMUs. all right, atomic mass units. So there you go. And you can see that it comes out closest to the 207 one. Why? Because it has the largest percentage. There you go. All right, again, I'm just putting each one together. I'll do one more because I feel like we don't need to go too crazy with this. So I like this one. It has silver, Ag107 has abundance of 21.82, and Ag109 has a percent abundance of 78.18. All right, I'm already going to point out one little error here. Obviously, this should be lowercase Ag, okay, capital Ag, that's silver. All right, so this one, it doesn't give you like a very technical mass, so we're just going to use the mass number. So this will be a lot easier, 107 times, move the decimal point over twice, 0.2182 plus 109 times 0.7818 equals. And I'm sure you're all enjoying just waiting for me to calculate this. And I'm getting 108. Well, I'm just going to, 108.56. I'm going to go ahead and put a couple things in there. Okay. 108.56, maybe 108.6. All right, which makes sense. It's closer to 109 if I did round that, AMU. All right, because it's the higher of the percent abundance. And that's it. Okay, so just keep it simple. Okay, keep it very, very simple. All right, very good.